Good morning, everyone. We will start our session now, and our first speaker is James Powell, who is a Python developer with a lot of experience in developing in Python, I guess, and he's going to talk about generators with Python.
So, good morning, everyone. My task with this session is to raise the energy level in here a little bit. I can tell you that my energy level is a little bit low because I was up till 3 a.m. last night writing a little bit of code. I think we all find ourselves in that situation. The talk you're about to hear has some theoretical or conceptual content, but I should say as a reminder that as programmers, our job is to create these code artifacts that do something useful. So I just wanted to share with you a little code artifact that kept me up all night. I sit in a lot of meetings, and I have to schedule a lot of meetings, so I thought in 50 lines of code, can I write a little tool that'll help me figure out how to coordinate meetings? So I wrote this little guy. It took me about 3-4 hours to get this, but you can see, you can put in the different time zones, you can search for the time zones, you can go forward and backwards in time, and I thought that's kind of neat. So that's an example of something practical and useful that we can actually accomplish with code. So let's get into the theoretical. The title of this talk is Generators Will Free Your Mind. I'll give you a brief introduction of myself and then we'll dive right in. I'm James Powell. As you can probably hear, I'm from outside of Germany. I'm actually from Texas. I live and work in New York City. The notes for this talk, if you're interested, are on GitHub at DUTC. That's my handle. You can find me under this name through all over the internet. DUTC stands for Don't Use This Code. I thought I'd put the disclaimer up front and center. So I'm James at don'tusethiscode.com. I'm at don'tusethiscode on Twitter. I have a blog at seriously.don'tusethiscode.com. On IRC, I camp out on many of the different channels, like the Python channel, the Positive Python channel. On IRC, I'm DUTC, if that's available, for Don't Use This Code. If that's not, I'm from Texas, so I'll add an H on the end, and I'll be there as Dutch for Don't Use This Code, Haas. Come on, I gotta raise the energy level a little bit here. I usually attend these events representing a meetup group that I run, NYC Python. In my spare time, I actually have a real job. I work for the Python Quants. We ran a conference in March, which I'll show you a little bit about, and I have a couple of jokes to get everything started. But I just wanted to show you a couple of interesting things and to let you know of some events that are coming up outside of Germany. This is the meetup group that I run, NYC Python. It's a group that I'm exceptionally proud of. It is the largest and most active Python meetup group in the world. We crossed 5,500 members. We have 4 weekly events, 2 bi-weekly events every other Thursday. It is amazing and it is intense. One of the things that we're doing this summer is we're hosting a regional conference in New York. New York skipped the regional conference in 2013. PyGotham is on for 2014. It's in 3 weeks' time. We are all completely stressing out and freaking out about putting this on, but it looks like it's going to be an absolute blast. It's going to be amazing. So if you have an opportunity, or if you're going to be in New York in this time frame, you definitely need to attend PyGotham. It is going to be really, really cool. The reason that we took upon ourselves the ambition to run a conference was that separate from the meetup group and separate from NYC Python, I actually ran my own conference in March of this year called For Python Quants. And some of the speakers here today were speaking there. You can see this guy somewhere in the back of the room. And it was an event for finance professionals who wanted to talk about the application of Python to problems in the financial industry. It looks like For Python Quants will be back maybe this year in London. So follow me on Twitter for news, but there may be news about another Python Quants event. The Python Quants is a consulting services and product company for in the financial analytics space. One of the things that we do is we build analytics and infrastructure for hedge funds. This is an example of a fund that we're building all the infrastructure and analytics for. Additionally, we have a really cool platform called the Python Quants platform. Go to quantplatform.com. Now, some of you may recognize me. The first PyData talk I gave was at PyData New York 2012, and then I spoke at PyData Silicon Valley 2013, then I spoke at PyData Boston 2013, then New York 2013, then London 2014, then Silicon Valley 2014, and this is the 7th PyData conference I've spoken at. And I've given the same talk every single time. Actually, no, there's some new material for you today, and I really hope you enjoy. But to get the mood started, I want to share with you a couple of jokes. I couldn't really calibrate the amount of seriousness for the audience, so I put in 3 jokes to get you guys warmed up, just in case you need it. So have you guys heard the one about the broken pencil? Never mind, it's pointless. That's weak. Okay, we got another one. What do you get when you cross a joke with a rhetorical question? That's a punchline in itself. And then finally, what's the difference between ignorance and apathy? I don't know and I don't care. Okay, with that aside, okay, we got a little bit of energy out of you guys. Let's see if we can plow through that. The title of this talk is Generators Will Free Your Mind. And the broad themes of what I want to talk about are code as an artifact that's in motion. Code isn't a static artifact. It's something that evolves over time as the needs of the problem the code is addressed to solve change. That generators are a very useful mechanism for modeling these problems, that we can use generators to build models for our problems that are fundamentally different from other approaches that we take. And these approaches can produce very meaningfully different results. And then finally, I wanted to touch upon a topic that is very dear to my heart, which is the need in our industry for a new set of conceptualizations. And you thought I was going to say something really warm and fuzzy, but actually what I think we really need is a set of fundamental epistemologies and conceptualizations. And I'll try and touch on that a little bit. What I won't cover in this talk is what generators are. I've given 6 talks about what generators are. Basic efficiencies of why we want to use generators. They're more efficient in a memory sense or a CPU sense, and some of the deep theory. One thing that I think that we should keep in mind as Python programmers is that Python is a very practical language. It is not an academic language, it's not a theoretical language. And so generators as a construct exist in a variety of different languages, just like functional programming exists in a variety of languages. And some languages stress the theoretical weight of these constructs, of generators or of functional programming, and they go into great depth with things like monads and transformers and arrows. And Python tends to take these theoretical tools and apply them as directly as possible. So I won't go into some of the deeper theory of coroutines. But let me get started. One note for this presentation is that this is based on these following future imports. There's a lot of real code in this, so just remember these. And this slide got smushed with the last slide. But the first thing I wanted to talk about was, what is programming? And this is where I think we kind of need to build a better set of conceptualizations for what we do. Because we can sit down and we can take a problem that somebody asks us to solve, and we can write code to solve that problem. And it's generally effective. Like if you come to me and you say, I need to model this financial product and I have to trade it in this particular way, I can sit down with the team and I can build an infrastructure, and I can build tools to analyze, to backtest, to automatically trade this product, and some results are had. But what I'll see over the course of that project, over the years of developing that software and managing that team, is the same pathologies arise and the same problems arise in the process. And I think that the consistency of some of the pathologies that we see in programming suggests that our way of thinking of programming is flawed. And so the perspective I come from with regards to programming, my particular religion is that programming is an engineering exercise. What that means is the real world has infinite, irreducible complexity. And our job as programmers is to take that complexity, to extract features from the real world that allow us to make predictions or allow us to model important things that are necessary for some business process, to take those features and to arrange them into a consistent and tractable algebra, that is a set of objects and a set of operations, where we can define interrelations between the objects, we can define the relations, and we can induce, we can infer principles from these things. We can create a system that can have predictable behavior based off of a set of unifying principles. And then we employ tools like generators or functions or classes in order to model this algebra. And so generators here are merely one mechanism by which we can actually sit down and encode a pseudo-mathematical model that can be linked to actually solving a problem. I know that's a little bit heavy, but I think that's the real gist of what we're trying to do and the real point of generators. So you might say, why do I want to use generators? They're too complex. They add too much complexity. But the point here is that there may be irreducible complexity in the problem that you're trying to solve, and generators are just one way to express it. And what I'd like to motivate for you is that generators tend to be a very terse or parsimonious way to express that complexity. Oh, let me not install my updates during my talk. So, to really motivate this point, I want to tell you that your mind has already been freed. And your mind has already been freed by just basic constructs, basic concepts in functional programming. It's already changed the way that you think of code. So a simple example I want to start with, just to illustrate this code is in motion and that functional programming has changed your mind, is a little report. So you have some data set and it represents the amount of profit that different regions make for some company. And here, each region makes somewhere between -$4 million and $4 million, and it's random every time that you generate it, and that's more or less how a lot of large companies work. And somebody says, okay, print it out to the screen. So you write a little function here called output, and it takes the input, and it goes through each line, and it prints it out to the screen. This is the simplest code you could write. 3 lines, you're done, you go home, you watch your TV, you go to bed. But then somebody says, well, look, this output's really hard for me to read, and I can't see in the line, they aren't lined up, and kind of suck, so you go in there and you say, okay, I'll use this advanced string formatting, this new string formatting in Python, and I'll make sure that everything is left justified. And you can see that originally where you had 3 lines of code, now you have 4 lines of code, and it's slightly more complex. And now you have things like locale-based insertion of the commas to group the digits, because some places group 3 digits, and some places group 2 digits together, and the complexity here has increased by some amount. And yet you're still not done, because somebody looks at that and they say, well, we're running this code in a system where we don't have access to standard out. So we also want to write it to a file. Or we want to write it to the screen. Or we want to write it somewhere else. And so you add in a little thing that takes in a file name parameter, and now you have this block here that says, if you gave me a file name parameter, I'll open the file and I'll write it to the file. And now the complexity has doubled. I mean, you have twice as many lines as you had before, and all you can do now is put it into a file and you have it nicely aligned. But that's not enough, because it never is enough, right? This code always changes. So somebody says, well, we want to log this as well. So now you introduce a modality, which is if you have a to-logging parameter, then you log it to info using the logging mechanism subsystem in the standard library. And so now you can print it to a file and you can log it, and you do a couple of things. You think you're done, but you're not. Because somebody says, well, we want to be able to email it as well, and we want to send it out on an email. So you add in a to-email modality. So there's yet another mode in this. And this mode says, if to-email is selected, print it out. And also, you can see, at this point, we can't even fit all of our code onto a single slide. And yet, even that's not enough. Oh, this is the to-email part. And you can see, with the to-email, there's a fundamental change in the way that we write it. We have to collect, in order to send the email, we have to send it off to a function that takes the entire body of the email. So instead of looking at it line by line, we have to collect all the lines here. So we have one if statement here, one if statement there, and then another one down here that collects all the lines and calls a function called email that sends it off. And we're still not done. And at this point, we may step back and say something is wrong with this code. We've added all these little switches and all these parameters and all these toggles, and yet if somebody comes and asks me for one more thing, I have to, the complexity of this code will just explode. I can no longer maintain this. And we reach for basic approaches in functional programming to solve this. So I'm going to skip over this slide because this is something that's necessary for the next slide, but it's a little bit of meta-class trickery to make this work. But you end up, it's not that wild, but you end up writing 5 lines of code that allows you to capture all of the complexity of those previous 20 lines of code. And you say, well, instead of taking all these flags like a do to log or a file name or a to email flag, I'm just going to take some function, and I'm going to pass the results to the function, and the function can take care of things. And instead of handling things like formatting, I'm going to have some template string, and I'll pass it to a template string. And you can see with this example, we can encode all of the complexity of the previous example with substantially less code. We could pass it a function that does the email and the log. We can even add additional functionality. We can inject additional functionality into this that we couldn't in the other one without having to add more modalities, more if-else blocks. So this is an example of how functional programming has freed your mind. It frees your mind from presuming modalities. In that 20-line example, you had to know the modes that your function would run in. You had to know that somebody might ask for you to email it or not, that somebody might ask for you to log it or not, that somebody might ask for you to write it to a file or not. Whereas in the functional approach, you don't presume those modalities. You accept the function, you process your data, you pass it to the function, and those modes are now the responsibility of the person who's calling your function. So you've been freed from having to presume certain modes of how that function works. Additionally, your API has been substantially reduced in complexity. It's been simplified dramatically. If you look at the previous example, look at all the toggles and flags that this took, and all the different ways that this could work. And if you had to test this, think about all the different combinations of these features you'd have to test to get complete code coverage. Because maybe there's a bug if you do toLog equals true and toEmail equals false, and the file name does or doesn't exist, or is on a different is on a different mount or something like that. And there's all these different modes you'd have to test. Whereas in the functional programming example, you just have to test that when you pass it a function, the results are passed to that function, and that function then is an independent unit that can be tested as a unit independently from this little output guy. And the API has been dramatically simplified. The amount of things that this function can do by itself are much fewer than originally. Additionally, I would say that pure functional programming may have further freed your mind. If you've gotten into some of the more theoretical aspects of functional programming, you might see that this example is maybe a little bit degenerate in the sense that a pure functional programming approach would tell us we shouldn't mix side effects with functions, and they should all be pure, and this allows us to do things like equational reasoning. But I don't really want to get into that, because I think that just these basic examples show us that we can implement a lot of functionality with just passing first-class functions around, passing lambdas around. And this is something that we already have internalized, that already works very well for ourselves. So with that being said, let's get into generators. And I told you I wouldn't tell you what a generator is, but I'll tell you what a generator is, because might as well. So let's start with a function. This is a function, and it's a really simple function, and it has a couple of properties, some formal characteristics, and some properties for how it works and how it looks, and we should all be familiar with it. This function gives you the elements of a Fibonacci sequence it gives you n values of Fibonacci sequence. And you can see functions have one input and they have one output. They may have multiple paths to that one output, but they have a single input and a single output. They are evaluated eagerly. So when you call the function, it's evaluated and you're done. And in a formal fashion, because they're eager, you have to collect results. If you have multiple results, you have to collect results. You have to do all of your computation up front. And in Python, this means you have this return keyword. And that's what generally distinguishes a function from a generator. This isn't quite true with Python 3.4 and beyond, where generators can now return objects, but generally the distinction was the use of a return or a yield keyword. And I'll show you another function. This one's called ratio, and it takes another sequence and it tells you the ratio of adjacent terms. And so if I run this over my Fibonacci sequence, we can see my ratio. It goes 1 and then 2, then 1.5 and 1.6. And if I remember from grade school, the Fibonacci sequence converges to the golden ratio. So we can see this here. We have a comprehension, and one part of generators in Python is generator expressions, which are very similar to list comprehensions, a dictionary and set comprehensions. So you can see what that looks like in a formal sense here as well. And you can see as we get subsequent terms, they slowly converge to the golden ratio. Now I think this is actually kind of neat, because whenever I'm traveling outside of the United States, where people use kilometers instead of miles, I actually make use of the Fibonacci sequence in that they're about 1.609 kilometers per mile, and the golden ratio is about 1.6, which means, and I think this is kind of cool, adjacent terms in the Fibonacci sequence approximate the conversion from kilometers to miles. So 2 miles is about 3 kilometers, 3 miles is about 5 kilometers, and so forth and so on. That's actually kind of useful in my daily life. If somebody says, somebody, you know, every time you give a talk and you're away, you say, I'm X thousand miles from home. And now I could maybe potentially say I'm X thousand kilometers from home. Unfortunately, being from Texas, my geographic skills are so poor, I really have no idea where I am right now. No, it's a joke. Okay, So let's get into generators. This is the exact same Fibonacci sequence, but implemented as a generator. And from a formal perspective, you can see instead of a return, we have a yield. Additionally, you can see we're not doing the calculation eagerly. We're doing the calculation lazily. We do each component of the calculation, and those components are returned as we ask for them. We can see that there is a potential for, there's one entrance, which is you call and construct the generator object, and there are multiple outputs. Each time you try to get a value from it, each time you iterate through this, you're performing a computation and getting a separate output. This is what we mean by a coroutine. It's a generalization of a subroutine, and that a subroutine has one entrance point and one exit point, whereas a coroutine has multiple potential entrance points and multiple potential exit points. We won't go into, actually we will go into full coroutines with send a little bit later in this talk. You can see also, very interestingly, in the first example, we presume something, which is we presume that you want Fibonacci numbers, you want 10 Fibonacci numbers, not Fibonacci numbers up to, but not greater than some number. You can see here, the control of which of the values we return is up to the caller. It's no longer presumed by the person who wrote the library function. So here we use islice from itertools in order to pick out the results that we want, to only get the computations that are meaningful for the problem we're trying to solve. Similarly, we can, this is an illustration of a very, very useful module in a standard library called itertools, which when combined with generators can result in some very, very useful helper functions. This is a helper function which I can write from memory these days called NYC. It gives you pairs of a sequence, so if you have a sequence from 1 to 10, it gives you 1 and 2, 2 and 3, 3 and 4. I use it in every single thing. You can see, look, even last night at 3 a.m., I figured out a way to stick it into this guy here too. So it's a very useful little generator, little tool. And you see I have my ratio as well. And then I can do my phi and all the results are the same. So I think if we were to try and draw a similar analogy for generators to what we saw with functions, with basic functional program, we can say that generators can free us from some presumptions about the way that our code is used. As I said, in our Fibonacci sequence, there are different ways that we could write it. If you look at interview questions, sometimes when this comes up in an interview, some people say, print the first 10 Fibonacci numbers. And some people will ask, print the first Fibonacci numbers that aren't larger than 10. And you can see we have two implementations. This is the first 10, and this is the first that aren't larger than 10. So here we get 10 numbers here, and we get the numbers up to 8, but no greater than 8. And you can see that these two look very different. And if somebody asked you to implement both of these behaviors, you might have to write either one very complex function or these two functions. Whereas in the generator example, your generator is the same. It just yields an infinite sequence of Fibonacci numbers, and then from the outside, you're able to use itertools, these helpers from itertools, to pick the numbers that you want. So you can pick the first 10, you can take as long as the numbers aren't greater than 10, but you can also implement predicates of arbitrary complexity. So what if somebody said, we want you to write a Fibonacci sequence, or a function that yields values from Fibonacci sequence, where you take them you want all the numbers that are greater than 5 and less than 100 and odd, and if it's Tuesday, do this, or if it's Tuesday, give me the numbers +1. And in the function, you'd have to do a lot of work to capture all those different modes and all those different ways that the computation you're doing could be used. Whereas in the generator example, all of those modalities are exposed to the person who's calling this function. So you can use drop while, take while, islice, and here you have all the Fibonacci numbers in the Fibonacci sequence. You have the first 15 subsetted by the ones that are greater than 5 and less than 100. And that would be very hard for you to encode in this functional construction. Additionally, you can think that because a generator is lazy, you only pay for the computations that you want. So let's say that I have this little function that does a little sleep, does a 1-second sleep. In the generator example, if I only want the first value of this, see there's an X range here 10, right? If I only want the first value, I'm only paying for the first computation. I'm not presuming how much of this computation that you want. And one example that I bring up a lot that I've seen is I was dealing with a trading system, and that trading system could give you all the trades that were done in a book. And this book had millions of trades. It was a very, very high volume trading desk. And I wanted all the trades that matched I wanted like 5 of the million trades, just the ones that matched a particular signature. But the way that this had been written, there was a function that was called, and it went to the database and pulled all the trades and returned them to me. And every time I called it, I'd run out of memory. It would just try to keep pulling trades and trades and trades, and it would build this list in memory and get larger and larger and larger and larger, and I'd run out of memory before I even got a return value from that function to then whittle down to the 5 trades I wanted. And if this had been implemented as a generator, it could have yielded values, it wouldn't have produced this memory pressure, and I could have gone through those computations up until I got the ones that I wanted, and then I wouldn't have to have paid for the additional redundant computations. Additionally, I would say that generators free you from a lot of other presumptions. Presumptions in the way that you encode the problem, presumptions in the way that you write your code. Presumptions like, what is my return type? If you have some function called process, it takes some input, it does something to the input, and it returns some value. You might want to return that value as a list, you might want to return it as a set, you might want to return it as a tuple, and you can see we have different ways to call it. We have different ways that we can write this out. In the first, we have a list that we append to. In the second, we have a set that we add elements to. In the third one, we have a tuple that we append to. In the Fibonacci example, we have our Fibonacci written as a function, and it returns a list, and we might have to convert it to a tuple or a set if that's what we really want. And we have to pay for that conversion as well, so you can see there's some timing here. Whereas, if we were to implement this as a generator, the generator gives you values, and it gives you values absent any notion of what the collection type that it's returning. So you can take those values and you can stick them into a list, a tuple, or a set. And this can be more memory efficient because you don't have the pressure of the 2 elements of memory at the same time. Here, if you had a very large sequence of numbers, you'd need to have the list of them while you're constructing the tuple, and then you could throw away the list. Whereas here, you're just getting values and you're dumping them into the data structure that you want. And you can see in this case, this took a couple of times to run before the times really came to where I wanted them to look like. But you can see, in some cases, this can actually be more time efficient to just put the elements into the data structure rather than creating a redundant data structure and then doing a value construction and the conversion. Additionally, I'm sure we've all run into code that looks like this. Somebody wrote an average function, and it takes a bunch of numbers, and they put at the top, if it's not a list, blow up on you. And you kind of got a little bit upset because you had your data in a tuple, and it was a really big set of data, and you didn't want to do a list on the tuple just to make this guy happy. Because why does this function care if it's a list or a tuple or a deck or a queue or any other structure? All it cares is that sum works and len works, right? But for some reason they said it must be strictly a list, and this bugged you. And you gave it a tuple and it blew up on you with a fairly pointless error. It said, we have to have a strict list. And you might say, well, I'm going to be smarter, and I'm going to say, since I need sum and len to work, instead of asking for a strict list, I'll ask for a size. I'll go into collections, and I'll use these abstract base classes, and I'll ask for anything that responds to len, and by virtue of responding to len, it probably can also be iterated over, and if it can be iterated over, the values can be summed up. But this won't work, because what if I have a stream of numbers? And you can give me the average of a stream of numbers, even if you don't have all the numbers available at the same time, even if you don't have the ability to look for the length of the numbers. And so, if you were to do that, this is our even more generic version of average. So instead of asking for a size or asking for a strict list, you ask for an iterable. All you care is that you can iterate through these numbers. And you only want to capture 2 things: how many numbers you saw and the sum of them. And so you can do it in one line if you want to make your coworkers hate you, which can be a very reasonable thing to do sometimes. But you can collect the sum, and you can collect the count without having to hold in memory more than one of those values at once, and you can return the average. And what this gives you is this gives you an average function here that can work on anything that can be iterated over. Here, you wrote this average function, and it presumed that you needed to give it a tuple or a list or some concrete collection. Here, you're able to free yourself from requiring a concrete collection, a collection that exists in memory at the same time. It'll work on anything that can be iterated over. And for bonus points, see if you can figure out how to write variants. It's a little bit trickier. This is an interview question that I've asked people if I wanted to give them a little bit of grief. Finally, you guys need to, raise the energy level a little bit in here. So I may have to go for a couple of jokes at the end if I don't see more smiling faces in the audience. I will say one of the most important things I think that generators allow you to do is to simplify your APIs and remove presumptions about modes. In our exploding complexity example of printing out this little report, you saw we were adding all these flags, and we were flags upon flags upon flags, and each of these were modes, and they corresponded to if-else blocks in our code, and that caused our code to be more indented. It caused us to have more and more code paths, more things for us to test, more area for bugs. It also required that somebody my goodness, you guys must have used pandas, and how many different toggles and switches are there in pandas? Oh my goodness, and half of them aren't even documented very well. And sometimes you look at the signature, and it just takes a star quarks, and you're like, what on earth can I do with this, right? The API is just immensely complicated. And you can see that this is very difficult for us to meaningfully use because we have to guess the interrelation between all the terms. Another example that hit me last night was argparse has all of these different flags. And my goodness, what are the interactions between all these flags? What does the default flag mean when you use the append action? It can be very, very complicated to keep track of all of those different things. So I'll show you an example of that. Here's a very, very much a toy example. And the toy example is you have some source data, which is a generator that yields an infinite sequence of random values, and it sleeps for some amount of time. So it represents maybe loading from a database or loading from a stream, some process where you get data and you have to pay for that computation to get the data. And some process here that does an averaging of it. So you can see for every data you have, you do a averaging of the set of the data that you have at the time. And in this process, this models kind of the idea that you have some long-running process that has some sleep in it, that returns a value, and that gives you subsequent values. Rather, some process that can give you, how should I say this? Some long-running process where you may want to look into it and see where it is along the process, or where it is in its computation. Because if you were to run this over a list of 100 numbers, you might sleep for 50 seconds. You might not know whether it's completed, whether it's finished, whether it's just started, whether it's hanging. And you might want to add in the ability to see where it is. You might want to add a little logging here to say, okay, I'm 0% in the process, I'm 20%, I'm 40%, I'm 60%, I'm 80%. Oh, now I'm finally done with all of my loading. And you might realize that, you could do that very easily by just adding a little print statement here where you print out, if you know the total number of elements you're loading and you know which elements you're on, you print out something like that. So you can figure out, I'm 20% through, I'm 40% through, I'm 60% through. And you might also find that you want to print out some message before and after. You might want to say, okay, I've started my data load, and now I'm done with my data load. And we see this all the time. How many times do you have some application that needs to load a lot of data in the background, and it pops up a splash screen, which is your initial action. It updates a little progress bar, and then when the splash screen is done, it gives you access to the application itself. And that's what you might do if this were a function. And you might say, I'm going to use what I learned in the first part of this lecture to add the ability to do all sorts of custom progress updates. So I'll do this in terms of a set of functions. I'll have a before function, a during function, and an after function. So when I'm doing this load data process, I'll call my before function. Then with each element, I'll call my during function, and at the end, I'll call my after function. So here, I'll pop up my splash screen. Here, I'll update the little progress bar, and here, I'll say, all done, ready to use. But you can see this creates an API of sorts. Namely, you have 3 arguments here, and you have to know certain assumptions about those arguments. So they're all functions, and the functions will be called in a particular order. And here, if you look at the way that I've called them, I have a bug. I accidentally put the before function, I actually used the after function for the before, and the before for the after. And there was no constraining me from doing this or not doing this. There was nothing constraining me from making this mistake. The API here was too unbounded. There were too many choices. I could give too many different possibilities to this. Generators allow us, or coroutines allow us to reduce our API by giving us a structure, by giving us a mechanism that really only has a very limited structure. A generator can be created, it can be iterated over, you can send values into it, and that's it. It's far more constrained than just a bunch of functions. So here's an example with a coroutine where instead of giving it a generator, you give it a coroutine, and the coroutine enforces a certain ordering of these elements, that you do the before, then you do the during, and then you do the after. Similarly, one problem that I see come up a lot is holiday calendars. And for holiday calendars, this is a holiday calendar for Japan. You can see they have a lot of holidays in Japan. They take off American holidays, they take off UK holidays, they take off their own holidays. It's probably a fairly nice place to work if you want to work in the finance industry. And typically, the way the holiday calendars work is that you do some double while loop here in order to get the values out, and you might want to get out, starting from this date, what's the nth business date going ahead to skipping weekends and holidays. But you could think that if you wanted the one business date off, the second business date off, and the third business date off, you're incurring the cost of this computation, this inner while loop, multiple times. You've made a presumption about how somebody wants to use this function. You've presumed that they only want to get one value out. They don't want to get a sequence of all the holidays going forward. And you've forced them to incur a lot of redundant computations. If you were to implement this as a generator, you can see instead of giving a strict value, you could yield an infinite sequence of of business dates going forward, and then the user could be free to collect these values as they desire. So they could get you give them an infinite sequence of business dates starting from this point, and they get the next date, the next date, the next date, and they only incur the computation that they need, and they only need to go through this while loop once. Now, bear in mind, there's actually a closed form solution for this, which I really need to write a talk about. I'm running out of time already. And you could say if I wanted to make this example more complex and I wanted to be able to go forwards and backwards with business dates, I might use what I learned from the first part of this talk, and I might give a direction, which is actually a function, and that function adds or subtracts time deltas to either go in the forward direction or the backward direction. So this is going in the backward direction with previous business dates. And you might say, well, if I want to do something more complicated than that, I want to do business dates where or rather, you can see that the complexity here is actually already fairly large. And if I wanted to implement this in a much simpler fashion, you could see that I could actually create a combination of two generators. I could have one generator that just gives you dates going in one direction or the other, and I have another generator that takes that sequence and takes a sequence of holidays and gives you the values going through that, and when they line up, when the next date is a holiday, you align it from what you get. So let me skip ahead. And you could say that if this holiday calendar were in an SQL database, as it often is, and there were some timing necessary in order to actually pull these values out, you have to do a query for each next row for the subsequent holidays that you want. If I wanted the next 3 business holidays, I don't want to do 3 separate queries to jump over the same dates. With the generator formulation here, you don't do that. You create one generator object, which has one handle to the database, that only does a query as you ask for the next dates, and is able to retain some memory of the last dates that are looked at. So you can free yourself from having to incur redundant computations. So the last example I want to show you is how generators can really fundamentally change the way that you write your code. Here's a function that calculates the amount of change that you need to return to somebody given a set of denominations and an amount. So if somebody asks for $1.72 and you have these denominations, you give them this. And maybe somebody says, this doesn't capture the problem I want to solve enough. I want to be able to figure out how much change I give if I have a finite number of coins, if I only have 5 $1 bills, 5 50 cents, 5 25 cents. And so the complexity of this arises again because now you have to count how many have I already given out, and you can see our complexity is exploding here. And this may not be enough because you may find that the requirements for this may be you can only give a certain number of pennies or a certain number of coins if you haven't given other coins, and the problem can become more and more and more complex. And I'll show you how generators can allow us to implement this in a very interesting and very different fashion. Think about the process of counting change. You have choices that you make from different objects, from different denominations, and you pick from the top denomination until you can't pick any more. You pick from the next one, then you pick from the next one, you pick from the next one. So you return dollar bills until you can't return any more dollar bills. Then you return 50 cents until you can't return any more. Then 25 cents until you can't do any more, and so forth and so on. And the constraints for how many of those you return may be that you have an infinite number of dollar bills, or maybe you have only $3 bills in your register. What we could do is we could use iter tools to construct this guy. And this is greedy. What this says is you repeat a certain number of items an infinite number of times, and you take those items while some predicate is true. And then you chain all of them together to get the result. Oop. And what you could do is you could implement a coroutine here that gives you that gives you a result for this predicate that says you can keep taking them as long as you haven't gotten until you exceed the maximum that was set up. And with this, you could do something like this, where you randomly generate a bunch of dollar amounts, you have your denominations, you create your predicate, and you just figure out the coins. And this is just another implementation of the first one, counting change. What I want to show you that's very powerful is this greedy algorithm is just a greedy algorithm. It's all it is. It's just giving you values by taking until it hits a local optimum and then proceeding. And as a result, unlike the original formulation here, where we were specified to actually counting change, this code is no longer specified to solving any specific problem. It could do things like figure out conversion between Roman numerals and Arabic numerals. And you could actually solve any problem that can be modeled by this greedy algorithm with the exact same code. And so it shows you that with generators, you have the ability to create, just as with functional programming, you have the ability to create these very simple, abstract, but very different structures that can create code that frees you from presumptions about return types, frees you from presumptions about how people are going to use your code, frees you from presumptions about modalities, and frees you from having to know how the code will be used. It empowers your users. So with that said, I think I've run completely out of time. I want to say that generators have freed your mind. I want to encourage you to all go in peace, and this is how you can contact me. I apologize if I rushed through the last few examples a little bit, but I was. Nobody? Yeah? No. By virtue of me having written it, I would say, well, yes, I think so, because you can say that sometimes abstractions can take you too far away from solving the problem at hand. But I think sometimes abstractions give you the ability to do more with less. So even this example is a little bit complicated. You can see that I have a coroutine here called predicate, and this predicate is very, very, very abstract. It just allows you to define a constraint function. It allows you to just pull values. And you could think that this is almost a mathematical structure, right? It's almost a mathematical construct, where it doesn't really seem to do anything immediately useful, and it does something at a level different than the actual level of solving the problem. It doesn't help you count out that change. It's just a piece for solving that. So should you write your code in this way is a very hard question to answer. But I think that if you were able to write your code in this way, especially if it were library code, you might avail yourself of opportunities to implement behaviors that would otherwise be too complicated or too involved for you to implement with the standard approaches. I think your question was a joke, but that's a serious answer to it.
Anyone else wants to ask?
So thank you for a very nice introduction to generators.
You're welcome, Francesca.
Yeah, so I like the concept of generators. One thing that I don't perhaps like that much is the performance. I mean, when you are into the data things in Python, you typically use NumPy a lot, right? Or extensions written in C. And I mean, in my opinion, generators always execute in Python space, right? So can you say some words about the kind of performance that you can expect from generators, and if they mix well with packages like NumPy or Pandas or things like that?
So So this is absolutely true. If you have some gigantic data frame and you want to do operations on the data frame, you typically won't do dot apply and pass. You won't use generators because you'll want to avoid having to reach into Python, to run any code in Python. You want to run code otherwise. What I'll say is generators are, the previous talk on generators went over things like performance. And you could see that performance of a generator is not actually that good. Sometimes you can write your code naively and it performs better. And that's because sometimes the overhead of constructing the generator object itself is greater than just having a function and calling the function. So in the other generator example, there's actually in the other generator presentation, there's actually let me do IPython notebook. So I'll show you in this presentation, there's actually an example of some code where it actually works better when it's written in a very naive way. What I would say is generators, I like to talk about generators as a mechanism for conceptualization, because it's a way for you to arrange and structure the code. And in this talk, once this loads up, I'll show you the example. You can see, so the example is down here where we have, time it, you have something that tries to do trial division to find primes, and it's done with little generator comprehension here, and it takes 2 seconds. And it's done here with just some run-of-the-mill Python, and it takes 1.3 microseconds. So writing it this way is actually much better than writing it in the generator way. And this is something that we see. The time to execute, or the time complexity or the time efficiency of a generator is not always that impressive. However, my counterpoint for that is generators force you to restructure your code in terms of these opaque computational blocks and the composition of those computational blocks. And they allow you, or they encourage you, as a result, to structure your code in a way where you can address performance more naturally. So the counterpoint to this from that presentation is also that when you get to the point where you say this code isn't fast enough, you profile and you say it isn't fast enough, by virtue of having constructed your program in terms of these streams that pass data to each other and that are these building blocks, you can swap out the building blocks with implementations that are faster, with things written in C. And I had an example of here a way you could swap out the NYC one with something written in C, and it's 100 lines of mostly boilerplate. So the answer is yes, in practice, generators aren't faster than other approaches, but they encourage you to write your code in such a way that you can swap out slow parts for faster parts later, as opposed to this giant mess of functions calling each other, which is what most code seems to devolve into. Additionally, generators give you whole program information, so a sequence of generators calling each other, they can see each other, so you can do optimizations on the whole program that you couldn't do with functions. Since functions are eager, they only see the value. Outer functions only see the values of the inner functions. Generators will see the inner generators. So you could do optimizations on that. You could have 3 generators in a row replace themselves with a generator that is an optimized fused version of that. So you could do ad hoc stream fusion type things.
Okay, thank you. Sorry, I would like to ask you to ask your questions offline because we are running out of time. So let's thank our speaker once more.